lecture, and we are in lecture 9, which is kind of putting everything together in terms of mechanics and talking about Wheatstone bridge and strain gauges. So we are going to connect kind of all this linear elasticity theory that we developed, how we relate, stress and strain, and all these kind of fundamental equations. So J equals E times plus nu, sigma ij minus nu, sigma kk, Kronecker delta, et cetera, et cetera. All these amazing fun equations that we learn in mechanics, and now we're going to learn how to kind of measure these things experimentally with strain gauges. So we're going to have basically a material. We're going to put a strain gauge on. A strain gauge is going to basically be basically wires, and we know that there's going to be a change in resistance as the length of those wires change, and we're going to derive these equations today. So we are going to kind of relate an output voltage, which is going to correlate to a change in resistance, which is going to correlate to some strain that we measure. So we're going to get this fundamental expression of the change in the output voltage as a function of, or not proportional to, but it'll be as a function of strain. So that's how we're going to actually experimentally measure strain. So electrical strain gauges have a long history. So first discovered, basically resistance of copper and iron wires will change when subjected to a mechanical load, or equivalently a strain. So I think this was actually first found in basically by Rouge and Simmons and patented at MIT a long while back. So we're going to correlate again the change in resistance. We're going to measure that change in resistance using Wheatstone bridge configuration, and that's going to allow us to kind of measure strain. So there are lots of different methods of actually measuring strain. So you could use an extensometer, where it's basically like you have a material and you have like this mechanical clip that you clip on, and then as you stress your material, you could kind of measure how this extensometer changes in terms of length. You could use kind of these optical techniques, photoelasticity. You could use video extensometry, where you're tracking dots on your sample. But again, typically we're using these strain gauges to measure strains in these kind of complex orientations, or especially if you have like, for example, if you're looking at a weld and we want to measure what's the stress state near that weld, we can't really use this linear elasticity theory. Instead, we're going to measure that strain experimentally with a strain gauge, and it's basically easier to apply a strain gauge than using some of these other techniques, especially the video extensometry, where you have to really calibrate your sample, and it takes a lot of instrumentation. So strain gauges, as annoying as they may be to kind of apply to material, are still commonly used a lot in industry and also in academia. So let's go ahead and start off with the basics of what happens when we stretch a material, or what happens when we stretch a wire. So the resistance of our material or a wire will change when we subject it to some type of external strain. So let's think of an example of, we have a copper wire, or just some wire. So that wire is going to kind of correlate to, on our strain gauge, we typically draw these lines. So this is kind of a zoomed in version of this wire. So we have some wire that has some diameter d, some length, I call it L here, and we could calculate basically the change in that resistance. We know that, again, if we subject the wire to uniaxial tension, the length of the wire is going to increase, the diameter of the wire is going to decrease, and we're going to get a change in resistance. Specifically, the resistance will increase. So we can calculate resistance using kind of this expression here. Hopefully you've seen that before in circuits. And if we want to see, okay, how does the resistance change as a function of these different parameters, resistivity, length, and diameter? Well, we can figure that out using our old friend, the chain rule. So if we apply the chain rule here, we could get this expression. And after several other, so again, this is just our wire subjected to this stress state, we should expect this resulting strain. So if we follow through with our chain rule and just rearranging these kind of math operations and then dividing out by r, we'll eventually get this expression right here. Now, there are a couple unique parameters here. What is basically dl over L? That looks similar to delta L over L, which in this expression, in this kind of coordinate system here, would be equivalent to the strain in 1, 1. We also see that dd over d is very similar to delta d over d, and that would be equivalent to the strain in the, let's look in that direction, the 2-2 direction. And I also know that my Poisson's ratio is going to be, again, the lateral contraction, so the lateral contraction minus E22 over the axial strain, E11. So you can kind of see that kind of holds out. You can kind of write that, see this expression right here. E11, so also minus 2, 1. So we can rewrite this expression that we have right here, plugging in these values, and actually we could also solve for one of the another key parameter, which is called the gauge factor. So the gauge factor is typically it's going to be given to you when you work in strain gauges for a lot of the problems that we're going to work with. Also, if you buy a strain gauge, typically you could find the gauge factor. The strict definition of this is other gauge factor is the following. So plugging in and just again rearranging, you could kind of put this in for E11 as well, but actually this should be dl over L. But that's essentially what we have here. So this is the gauge factor. This equation might look a little bit messy, but we get this really nice expression between gauge factor and this right here. So if we rearrange this expression, we're going to get to one of the fundamental expressions that we're going to utilize in this course, which is, again, what do we want to do initially? We want to measure strain experimentally and correlate that to a change in resistance. And from this expression here, from this just general idea of stretching a wire, we see that the change in the length of my wire is proportional to this kind of change in resistance over R and this gauge factor. This is it. This is our fundamental expression for how we're going to correlate, strain to the change in resistance. And we can see here, if the strain is tension, if it's positive, we're going to get a positive change in resistance. Why? Because our wire elongates. So our wire goes from here to here. It goes longer, thinner. I'm trying to show thinner. So now my ions have less, my electrons have less room to kind of move around. So it's going to be more difficult to move. My resistance is going to increase. This is our fundamental expression right here. So now you might be asking, actually, because you're going to see this kind of same thing. Now you might be asking, well, why do we have to kind of, study and utilize this Wheatstone bridge configuration or utilize these circuits? I said at the beginning that we're going to kind of correlate the change in the voltage to strain. Why can't we just directly measure delta R? Well, the reason is if you plug in some of these values, it's going to be very, 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 we're going to be measuring strain or on the order of 10 to the minus 6, 10 to the minus 9. You're going to have to find an ohmmeter or, a resistor, to measure resistance. If you find an ohmmeter that has 0.00001, ohms sensitivity, patent that and sell it to me directly. So we have to use circuits because our ohmmeters don't have the precision or the sensitivity to kind of measure, the strain that we're going to be looking at in a lot of these problems. So instead, we're going to have to use a more precise tool, which is circuits, which are extremely, extremely precise. And it's going to give us the sensitivity and the relationships that we need in order to kind of solve these problems. So we're going to be going into kind of Wheatstone bridge circuits, actually just in the next video. So we need to kind of use the circuitry. Why? Our ohmmeter is not sensitive enough in order to kind of measure these values. So the key takeaway here from this kind of first video in the first lecture is this expression right here. So we see if we're in tension, my wire elongates, my resistance increases. If we're in compression, I'm going to see kind of, again, that a drop in that resistance. Again, my wire becomes more, thicker, shorter, and the resistance is going to be easier for those electrons to move through it. So that's the key idea here. This is our fundamental expression that we're going to kind of come back to quite a bit. So I'll see you in the next video where we're going to do some circuits and some voltages and hopefully brush up on some of our voltage divider circuits and then develop our Wheatstone bridge. So I'll see you in the next video. Thanks. Bye.